Welcome. In this video I'll discuss electron drift waves, and these are sometimes called the universal instability, and there's quite a long debate about when they're unstable and when they apply, but it's generally thought that these are essentially almost always unstable in plasmas, and they have a very simple kind of physical picture which I'll discuss here, and they're also quite useful as a starting point for understanding more complicated drift waves. Some of the concepts that we'll cover are the Boltzmann response, sometimes called the adiabatic response, which is how usually electrons, behave along field lines, and this links the density perturbations to electrostatic perturbations, and is involved in a lot of the drift wave dynamics. And then we'll go through the slab picture of drift waves, electron drift waves. So we'll start with the electron Ohm's law. So we just have electron velocity across, this includes the Hall term, the J cos B term, and the standard ideal MHD term. We have the other Hall term, the electron pressure term, which is the same order, and then we have an electron mass term, which I'll simplify a little bit. So it just has like a dj by dt here. The full expression is in a previous video, but it's a little bit more complicated. And here we're going to ignore this anyway. So we're going to assume that the electron mass is 0. So we're going to neglect electron mass. I'm just going to include or look at the effect of this term essentially. So it's the electron pressure along the magnetic field. So we'll take the parallel component of this equation. So we have things like, so we're going to base dot product this equation with the unit vector in B. And of course this term then vanishes, so the J cos B term doesn't enter into this, and so we just have that the parallel component, which is just B dot E, which is going to label E parallel, is equal to, here we have minus B dot grad electron pressure divided by En, and this gradient along magnetic fields, so B dot grad is sometimes just labeled partial parallel, so it's the gradient along the magnetic field, and so we can just write down we essentially just have these two terms here. Now for an electrostatic kind of wave, the electric field is just minus gradient of potential, so E is roughly minus grad phi. This is for electrostatic. And so the parallel field, so E parallel is roughly just minus B dot grad phi, which is we're going to label minus grad parallel phi. So what we do now is we look at what happens to small perturbations. So if you have a wave in the plasma which is causing density perturbations or perturbations to the potential, for example, how does this equation respond? And so we can just write down that the change in the electric field, so delta E parallel, is roughly just minus the partial gradient of the change in potential. And from this side, we can assume the change in pressure is mainly due to the change in density, at least for now. And so we're going to write down that so delta PE. And so we can put this into this expression here. So just substitute these two components into here, and we have minus grad parallel delta phi. It's approximately minus. Now here we have a grad parallel. We can take the constant E and T outside. So E T grad parallel N, so delta N. Divided by E times N. See these E's now cancel. So we have a parallel gradient of minus delta phi. And we take this over to the other side, and we just have we have a plus T over N times delta N, and that parallel gradient is equal to 0. And so we just essentially take this out, so integrate this up. And what we usually write down is that we have delta phi over T is approximately equal to delta N over N. So the change in density, or the ratio, the fractional change in density, is related to the change in potential. And this is due to the relationship between the plasma pressure, the electron pressure, and the parallel electric field, which is needed to balance Ohm's law along the field. And so if the density is changing slowly, the electrons have time to respond, and then the electrons will move around and change the potential so that this equation holds. So this is for long time scales compared to the speed the electrons move, so the inertial speed, or the plasma frequency of the electrons. So this is for long time scales, hence the adiabatic, because it's slowly changing as far as the electrons are concerned. And this relationship is used in many situations for drift waves, where typically you have one species which is behaving in this adiabatic response kind of manner, and then the other species is driving, producing the drive for the instability. Now, electron drift waves are one example. And if you try to draw a wave, so you have a kind of wave you have a gradient. So for example, if you have gradient of pressure here, so this is high pressure underneath and low pressure on top. And if you have a wave, and so it has a k vector, which is like this. This is the wave k, and there's a magnetic field which is at some angle to this wave. So it's not exactly perpendicular, not exactly parallel. But we have a wave which is something like this. So it's at an angle to the field lines. So this is the B field here, and so there's a k parallel. So here there's a trough, a peak, and then here the wave is at a trough, and so the pressure is varying along the field, as well as perpendicular to the field. So what's happened here is that we have if you have some small perturbation to the density, say, then what's happened here is that we have a high density here, and we have, say, a low density here. And so similarly, you have here you have a low density where the plasma has moved inwards, or the density has moved inwards across the fields. Here the density moved outwards, and so we have high density here, low density, and high density here. So you have just a small perturbation, which is like a wave. What happens here is that because we have a wavelength along the field, the electrons move along the field lines until their pressure is balanced by the electric field. And so we have this, because we have this adiabatic response, that delta n over n is roughly delta phi over t. What happens is the high n regions correspond to high potential, and low n correspond to low potentials. And so we end up with basically electric fields which go from high to low. So here we have E fields like this, and E fields like that. And these electric fields will produce E cross B drifts, and so this will produce this electric field will produce an E cross B drift, which is upwards, and here this will produce a drift downwards. And so what this does is it produces a wave which pushes the wave along in this direction here. So it's moving this part down, this part's going up, and so the wave propagates in this direction. So the phase speed moves like this. The E cross B velocity is moving upwards here and downwards there, and the whole wave propagates in the direction which is perpendicular to B and perpendicular to the gradient of density. So it's a combination of the E cross B drift caused by these electric fields, moving the density radially, and then that density corresponding to a pressure gradient along the field lines, creating an electric field. And so the interaction between the electron response along the field lines and the drifts across the field lines produce this wave. And we can work out the dispersion relation for this wave. So we have the continuity equation for the density. So we have d by dt of the density perturbation, and that's just the divergence of the flow. So n times delta delta V is the, or delta U I guess you could call it, is a fluid, so the perturbed fluid velocity. And here we're just going to assume that delta U is just the E cross B drift. So it's the E cross B, which is this E cross B drift here, which is moving the density inwards and outwards. And so this is just 1 over B and then B cross grad phi. And if we're going to write this down in terms of k's and omegas, what we can do is we'll label this direction is the theta direction, because typically in topic this would be the poloidal direction. And so if we map this into a torus, this is basically poloidal direction, and then this is like the toroidal direction into the page. And so this just becomes as like k theta over b. So this b cross grads, as is the gradient in the direction perpendicular to the field, which here is the poloidal direction, times the perturbed field. So this part here becomes a minus I omega. This part here, so if we ignore the compression of the E cross B drift, so this part is approximately the E cross B drift, so E cross B, dot the gradient of n, and then this gradient is effectively just the dn by dr. So this is the radial gradient, and so this is the radial E cross B. And then we can just use this component over here to write down, as then we just substitute E cross B drift into this component here. So this is the radial component of the E cross B drift, and this just gives, and then the other part is that so this is the expression for V cross B times the radial gradient of n, and then the delta n we can relate to the delta phi by using the adiabatic response. So delta n is just delta phi over t times n, and so we can get an expression for omega, cancel out the delta phi here and delta phi here, and we end up with a dispersion relation. So this has we can write it in a slightly different way. So this is basically k theta, which is the k in the poloidal direction perpendicular to b and n, times the velocity, sometimes called v star, and this whole thing is just called omega star. So this is a frequency, sometimes called the diamagnetic frequency. So these waves propagate at the speed v star, where v star is given by en b, and then this is dp by dr. So effectively just combine these temperatures together, move this inside to get a pressure, and this looks like a drift frequency. So it has the form of a particle drift or diamagnetic drift, but you can see it's come from quite different source. And so because the frequencies are like the diamagnetic drift frequencies, these are called drift waves, but you can see that the derivation has very little to do with the actual diamagnetic drift, and it comes about through the adiabatic response and the radial advection of density by E cross B drifts.